Hello, we're continuing where we left off with binomial expansions for fractional and negative powers, specifically looking at what could be viewed as the domain of valid values for that binomial expansion. But what do we mean when we say that? Well, let's take a look back at the formula that we were using before to find these binomial expansions. The formula looked like this, and it's in the formula booklet. Yet, if you look in the formula booklet, you might notice there's a little extra detail written in there, which tells you that this expansion is only valid for values of x where the modulus of x is less than 1. It's worth pointing out that this fact is only true when we are looking at binomial expansions that have fractional negative powers, and therefore you don't need to worry about any of this stuff if you're just doing one of the old school binomial expansions you came across before, like 1 plus x to the power of 3, etc, etc, basically any positive integer power, because those are true for all values of x. Anyway, for these particular binomial expansions, they're only valid for these values of x, but why? It's worth pointing out you don't really need to know the proof about why this occurs for Maths A-level, but I can in this video at least give you a general intuitive demonstration of the fact that they're only valid for certain values. So to understand that a bit more, the first thing we need to remind you about is the fact that the binomial expansion, when dealing with fractional negative powers, isn't your traditional multiplying out the brackets in that more traditional sense. Instead, you might have heard me describe it before as more of an algebra estimate for the original expression. Part of that issue comes down from the fact that these expansions are meant to be infinite, and of course, if you're writing them out, you're not writing out an infinite number of terms, for obvious reasons, so therefore because you're stopping the expansion earlier than you're meant to, then the expansion just becomes an estimate rather than a direct equivalence for the original expression. But it's also just down to the fact that we aren't directly expanding the brackets, and instead we're just finding a similar expression that does a similar role to the original expression without being the same thing directly. This can be viewed when you start trying to plug x values into these expansions, and you start to see the flaws about when they are or aren't so valid. For instance, let's say we wanted to plug x equals 0.1 into this expansion. Of course, if you're actually doing 1 plus x to the power of minus 3, plugging in x equals 0.1 would lead to this, and if you were to actually calculate the value that that comes to, you'd get 0.7513 to 4 decimal places. But let's see what happens if you actually start trying to use the expansion to estimate this value. Well, it depends straight away how many terms you use. So for instance, if we then just plug x equals 0.1 into just the first term of the expansion, well, that would be a bit silly because there's no x's to actually plug it into. So therefore you just have the number 1. But we can then improve the estimation by then increasing the number of terms in the expansion we're actually using when calculating the estimate. Let's say we plug x equals 0.1 into the first 2 terms of our expansion. In that case, you'll get 0.7. You can already see we're starting to get closer to the value we're actually trying to estimate, and this is just going to improve the more terms we use. If we now plug x equals 0.1 into the first 3 terms of the expansion, you'll get this, which leads to 0.76. We're getting closer still. What happens if we plug x equals 0.1 into the first 4 terms? You'll get this. As you can see, there's almost 2 aspects to this. The first of which is the expansion's getting more accurate the more terms you include. But the other aspect to it is that we can directly see that it definitely is heading towards the correct value. Each term we add on is just adjusting it a little bit more to get it just that little bit more close. And the more terms you did this for, you would start to see this just slowly and slowly get closer and closer to the actual value. I was using a value of x of 0.1 though, and you'll note that's a value of x that's between minus 1 and 1. But what happens if we use a value of x that's not in this interval? Well, let's use the same expansion again, but this time plug in x equals 2. Of course, that is outside of our interval that's meant to be our valid values, so let's see what happens. If you plug it into the original expression, you'd have 1 plus 2 to the power minus 3, and that as a decimal is 0.0370 to 4 decimal places, or 1 over 27 as a fraction. But then if you start trying to use the expansion to estimate this value, you start to see a problem occur. Plugging it into the first term of the expansion, again, that's silly because there's nowhere to plug the x, so you just have 1. Okay, that's not that accurate, but we only used one term of the expansion, and we know that from before, if you use more terms, it will get more accurate, or at least that's what we think. If we now plug x equals 2 into the first two terms of the expansion, we now get minus 5, which is a problem because it means we're now further away than we were before. But no worry, what happens if we include even more terms? Will that help correct the issue? Well, the answer is no. If you do it with the first 3 terms, you get 19. If you plug x equals 2 into the first 4 terms, you get minus 61. And you can very easily see that this is ballooning out of control. The problem is getting worse, not better. The reason for this is the further you go into the expansion, you're including higher and higher powers of x. And the problem is, if you take any number that's bigger than 1 to a higher and higher power, the number gets bigger and bigger and bigger. 2 to the power 4 is bigger than 2 to the power 3, is bigger than 2 to the power 2, so on and so forth. So therefore, that's a problem because therefore we're just making the number we get bigger and bigger and bigger. And if you continue this on forever, you're just going to get infinity, which of course would be an incorrect estimation for our original value. So therefore, that's a demonstration of the issues that occur if you start trying to use different values of x in these expansions. But ultimately, all you do really need to know is that 1 plus x to the power of n, where n is any fractional negative power, is only valid for the modulus of x is less than 1. However, an extra layer of detail worth adding is that the expansion gets more accurate the closer you are to 0. Although in theory, if you include enough terms, any value between 1 and minus 1 will technically eventually end up being an accurate estimate. Unfortunately, the closer you are to 1, the more terms it's going to require before you start to see that accuracy appear. However, with all that said, let's take a look at actually what impact this has on answering questions. The most basic thing they can ask you is to simply state the range of values for which the expansion is valid. In other words, to express the interval of values that we were just talking about. To do this, all you have to do is look at your binomial expansion, specifically inside the brackets, and check that what's inside the brackets matches what's in the formula booklet, which is that the expansion formula is valid for 1 plus x to the power of n. If it is just that similar structure of 1 plus x, then you can just directly quote what the formula booklet says and say that it's valid for the modulus of x is less than 1. Alternatively, you could write this as minus 1 is less than x is less than 1. That, of course, means the same thing as modulus of x is less than 1. But what happens if it isn't just an x inside the brackets? Because we've already had to deal with finding expansions of that type, but what impact does this have on the domain of valid values? Well, let's take a look. Ultimately, all you've got to remember is that in order to find expansions of this type, in this case we've got 1 plus 5x to the power of minus 4, because the x has been replaced with a 5x in the structure we were looking at before, then ultimately to find the expansion, we did the same with the formula. But if you're doing that with the formula, then the facts that are true about the formula also have that same effect applied to them. So instead of the modulus of x being less than 1, the x gets replaced with 5x, meaning we know the modulus of 5x is less than 1. The only thing we've got to do is then rewrite this to make it more clear that x is the subject of this range of values. So, students who are confident about manipulating expressions that have a modulus sign involved feel fairly confident and are just able to divide both sides by 5 to realise we have the modulus of x is less than 1/5, and that would be the final answer. If you are somebody who's confident with what a modulus sign means, then you are welcome to do this because it is the quickest way by far to find what the domain of valid values is. However, it's worth pointing out that for a number of students, this approach is not so good because it gets them into bad habits. Because that 5 is inside some brackets, they are modulus brackets, but those are still just special types of brackets, and normally we can't just take things outside of brackets for no reason. Sure, it does work this way with modulus brackets, but again, unless you are comfortable with what modulus brackets do, then you might not be quite happy with why this happens, and therefore also you probably will forget that you are allowed to even do this. So a better way to see what's going on is to go back to what we said before. I mentioned that the modulus of x normally means x is between 1 and minus 1, so if you're doing that substitution and replacement, what we're really saying is now that 5x is between 1 and minus 1. This now makes it more clear as to why we can just divide by 5, because we can divide by 5 on the inequality when it's of this format, and now we've got no scary notation, it's a bit more clear what goes on. If we divide 5x by 5, we get just x. If we divide 1 by 5, we get 1/5, but because we divided by a positive number, the inequality sign stays the same, and the same thing happens over here. Minus 1 divided by 5 is minus 1/5, and if we've divided by a positive number, the inequality stays the same. So therefore, this is an alternative way of writing the correct final answer, so choose which approach you prefer. However, if I have my teacher hat on, it's worth noting that although all the questions we've been dealing with so far have directly asked you to find the range of values of x which the expansion is valid for, even if the question doesn't ask that, it's good mathematical practice to just write this range of values anyway, anytime you're finding a binomial expansion with negative or fractional powers. Whether you're actually required to do this or not does vary exam board to exam board, and even examiner to examiner, because it depends on who writes these exam questions, so therefore I would recommend just getting in the habit of writing it anyway, because then you're not giving the examiner any excuse to drop you marks, and also you haven't really ultimately wasted much time if you do write it, because it's effectively just 1 second of working to calculate these things. So, looking at this third example, let's put that into practice. It just asks for the expansion and doesn't mention anything about the range of valid values. But therefore, we're just going to get in good habits and write it anyway. Of course, to find the actual expansion, that's the stuff we're doing in previous videos, and therefore for this we just realise n is equal to minus 3, and also we have to do a substitution where we replace all the x's in the formula with minus 6/5 x. So therefore the expansion would be 1 plus our n lots of our replacement for x, and then you would add on n times by n minus 1, all divided by 1 times by 2, lots of our x replacement, all squared. Cool. And then of course you would just simplify that expansion you've got there for the bulk of the rest of the question, but if we're also finding the domain of valid values, well, we could do that as well. This is again where you've got options. You could either just do the substitution into the modulus notation and realise the modulus of minus 6/5 x has got to be less than 1. This is again why I said before, this method is only really good if you kind of understand what modulus means, because technically what you'd next do is realise that the modulus means you can effectively ignore the minus sign in that particular area, but then simplify after that to get modulus of x is less than 5/6. However, to get a better understanding of why that is the case, let's take a look at it if you write it as an inequality. 6/5 x is between 1 and minus 1, and therefore we're going to divide both sides by minus 6/5. So technically 1 divided by minus 6/5 is minus 5/6, and minus 1 divided by minus 6/5 is positive 5/6. Well, that's weird because now we have the minus sign on the right and the positive number on the left, but then realise we've divided everything by a negative number. And that means when you divide both sides of an inequality by a guaranteed negative number, that means that you flip the inequality sign the other way around. So therefore this is the correct domain of valid values, or alternatively you could of course write it in the sort of more usual order for an inequality like this, but that of course means the same thing as the thing above. And in case you're wondering what the valid values were for expansions that don't have just a 1 plus some algebra inside the brackets, like for instance here we've got 3 plus 7x all to the power minus 2 for this expansion, a big clue of how we deal with the valid values goes back to how we deal with these sort of expansions in general. What we've got to do is realise the formula doesn't work if it's not just 1 plus something inside the brackets. So first thing we have to do is factorise 3 out of the 3 plus 7x. That'll leave us with a 1 plus 7 over 3 lots of x. But then, that's just us factorising the 3 out of that algebra. We haven't dealt with the power at all. So then, of course, you have to apply the power to the 3 and to those brackets, like this. And then therefore, of course, 3 to the power minus 2 is just 1/9. So all you have to do is find the expansion for 1 plus 7 over 3 lots of x to the power minus 2, and then just multiply the expansion by 1/9 afterwards. However, that therefore gives us a clue as to what the valid values are for it, because now this is an expansion just like the other ones we've just been dealing with, so therefore the valid values would be 7/3 x is between -1 and 1, so therefore x is between 3/7 and -3/7. Or alternatively, modulus of x is less than 3/7. Cool, just one more thing we're going to cover before the end of the video, and that is what happens if you have multiple expansions in the same algebra expression. Well, what you've got to do is you've got to find the values of x that work for all of those expansions. So you've got to choose an interval that is true for all of them. So, how does that look? Well, we could take a look at an example. We've got to state the range of values of x for which this expansion is valid. So what you could start off by doing is considering the different parts of the expression we've got and considering what are the possible values that are working for that particular part of the expansion. For instance, for this first expansion, well, we know it would be modulus of 2x is less than 1. In other words, x modulus is less than a half, or in other words, x is between half and minus a half. So I will write that down there as well, for those of you who prefer that method. And then for this second expansion, well, for that case, we know modulus of minus 6x is less than 1. So modulus of x is less than 1/6 positive. I've skipped a lot of working there, but if you follow it through using the logic we're looking at in the last slide, then you could also find that out. But if you do it the other way as well, then that would also lead to 1/6 and minus 1/6 being the numbers in your inequality. But therefore, what are the values of x that work for the overall expression we've got? What you've basically got to view this as is similar to what I did in my video on simultaneous inequalities. You're basically trying to see where do these two inequalities overlap. One of these inequalities is saying that the valid values are all the values between minus a half and a half. So if I have a number line and I start trying to shade that, that would look like these particular values here to here. But then the second expansion is only valid between minus 1/6, which is a bigger number than minus a half, up until 1/6, which is a smaller number than positive a half. And therefore that expansion is only valid between here and here. So therefore the only part that's valid for both expansions is this bit in the middle here. That's the only part that works for both expansions individually and therefore the expression as a whole. So therefore actually the final answer to this question is just that x is between 1/6 and minus 1/6. Okay, hopefully you found that useful. That is all we're going to cover in today's video. I hope to see you in a future video. Goodbye.